we may produce space temperatures lower than about negative 100 degrees Fahrenheit by mechanical compression cycles through cascade or binary arrangement. So this is the theoretical cascade vapor compression cycles. We may draw this, and we may draw its schematic diagram. So we have again a condenser. So we have this expansion valve, and on the other side we have this compressor. And we have now our cascade condenser. This is our cascade condenser. So at the lower loop, we have this one. We have this expansion valve here, and we have its evaporator. And we have this another condenser here. So we may label this one by this point is point 1, point 2, and this is our point 3, and our point 4 here, our point 4. So at the lower loop, to avoid confusion, we have to label this one as point A, and this is point B, passing to this expansion valve here. That is our expansion valve, and this is our compressor 1 and compressor 2. So this is point C, and this is our point D here. So for cascade vapor compression cycle, so we may use two types of refrigerants here, or either you can use the same refrigerant for the upper loop and the lower loop of our cascade system. So like for example, have to consider the R12, and in the lower loop we have this R13. Okay, so So this refrigerant will passes through here. Okay. And also this refrigerant will pass through here. So this is our upper loop here, and this is our lower loop. So as we consider the analysis for this system, it is quite similar with the single stage vapor compression cycle. We are to consider the upper loop as a single stage and the lower loop also as a single stage. Okay, so in here can be able to analyze the system by determining the its diagrams, like the pH and the temperature versus entropy diagram, or the pressure enthalpy diagram. Now, to draw the TS diagram here to be able to know the analysis of our system. So this is the temperature versus the entropy diagram here. Okay, so at the upper loop we have that one, and in the lower loop we have this one. So this is our point 1 here, and this is our point 2. This is our point 3. So we consider that as a single stage cycle. So we also assume that it is isentropic. So the entropy at point 3 and point 4 is the same, or is constant. So that is point 4. So in the lower loop here we have this one. This is our point A. Okay. And this is our point B, and this is our point C, which is this saturated vapor, and this is our point D. Okay, so as you can see, back to our schematic diagram here. So there are 12 passes to the expansion valve, and this is enthalpy is constant and passes to this cascade condenser. So we have here at point 2 and point 3. Okay, so till the suction, this is saturated vapor here, and passes to the suction of the compressor, and it will be compressed to given a higher to given pressure and temperature. The same is true within the lower loop. So to avoid confusion, we label it by counting numbers and the letters. Okay, so in the lower loop you have this point A, and passes to the expansion valve with the equal enthalpy, and it enters the evaporator, and here the state is at point C. The state also is saturated. This is saturated vapor. State is saturated vapor of our refrigerant. So this is the suction of our compressor here, and it will be compressed at a given pressure and temperature. So what we have in here is the temperature versus the entropy diagram. Okay, so going to analyze. So we have here the enthalpy. The entropy is constant here, S3 and S4, and also at the lower loop you have also, as we compress the refrigerant, also the enthalpy or the entropy is constant. So at the upper loop, this is our refrigerant 13 here, and in the lower loop this is our R13. Okay, for that is this diagram to for clearer discussion. So you are also to draw its pH diagram. Okay, so because example, you have your diagram, then able to interpret the data, or have to read the data on the pressure, the enthalpy, and the temperatures, entropy, and other thermodynamic properties of the refrigerant. So this is the here. This is our the upper loop. So this is the same as the single stage. Okay, so this is our point 1 and point 2, point 3 and point 4. Okay, so in the lower loop we have in here that one. So you have this one. Okay, So here we have this one. No, we have this one. So this is our point A here. This is our point B, and point C, and point D. Okay. So that one. Then we have here the enthalpy is constant, and also here this is constant. Enthalpy is constant. Okay, and the entropy is constant also, and the entropy at the upper loop is constant. So this is the refrigerant 13, and the lower loop we have the R12. No, it is this is R12, and this is R13, and the lower loop. Okay, this is R12, and R13. So we have now the TS and the pH diagram. Okay, so what's next? So here, considering the we have now this cascade condenser. So where to draw the cascade condenser, the schematic diagram. For the simplicity of our equation, we will consider the mass of our refrigerant in the upper loop and the lower loop to be equal to 1. This is our cascade condenser. So at the level we have point entering, this is B. No, this is point 2 here, and this is point 3, and at the lower loop this is point D. This point D, and at the exit we have point A. Okay, we have that point A. So looking at the figure, we have in the upper loop it serves as an evaporator, and in the lower loop it serves as a condenser. So the heat that is rejected here in the lower loop is absorbed in the upper loop. Okay, so you can say that for energy equation, this is constant. Okay, so the Q here, meaning the Q D to A. You know that the Q is a path function, is equivalent to Q from 2 to 3. That is our energy equation, or by first law of thermodynamics, that is considering it in the system, be able to assume that the energy in is equivalent to energy out. Okay, so the energy in here, we have what? The energy in is the point 2. This H2 and this one HD. This is equivalent to out, the energy out. So this is energy in, the energy out of our system. Okay, the energy out will be this H3 here minus or plus HA. So we can say that this is H2. So transpose this one, H2 minus H3, and this is equivalent to HA minus HD. Okay, so it is for our cascade condenser. So going back to our figure, so here in here we treat the upper loop as a separate single stage. You can do that, and also with the lower loop you can separate the analysis as the same with the single stage vapor compression cycle. Okay, to compute the coefficient of performance now, so we have the coefficient of performance. What is that? This is the effectiveness of our system. This is now the QRF over the work input. Okay, you have the work input here. So going back again to our schematic diagram, you have the QRF here. and we have two compressors, so we have two. This work on the compressor 1, and this is the work input. This is compressor 2 and the work input at the compressor 1. Okay, so this is QREF. This is the work of our work input of our compressor 1 plus the work input of our compressor 2. Okay, so what is our QREF in terms of the enthalpy? So our QREF here. So going back again to our schematic diagram, our QREF is this is our evaporator. So this is point B, point C, and we have our QREF. So energy in, energy out, considering a steady state, steady flow, our first law of thermodynamics. So we have our QREF here. This is our energy in. It is plus HB. This is equivalent to HC here. So therefore our QREF would be HC minus HB. So this is therefore HC minus HB. So for our compressor here, so we have for the compressor 12 or compressor 1, this is our compressor 1. We have out at this is 1, 2, this is 0.3, and this is 0.4. Okay, so this is the work of our compressor. Compressor 1, this is what? By energy in, energy out, we have compressor 1. Work of our compressor 1, this is plus H3 is equivalent to H4. Okay, so work of our compressor 1, this is H4 minus H3. And also for our compressor 2, so our compressor 2, we have this one. We have the work of our compressor 2, that is the work input, and the inlet is this one. This is B and C. So by energy in and energy out, we have in here the work of our compressor 2 would be this is HC minus Now this is point C. This is our point C in here, and this is our point D. So we have HD minus HC. Okay, so therefore we can derive our COP in terms of enthalpy here. So we have the QRF, that is HC minus HB, all over the work of our compressor 1 plus the work of our compressor 2, that is the total work input, is the total work input. Okay, that is compressor 1 is H4 minus H3 plus this one. This is HD minus HC. Okay, so considering the mass of our refrigerant, the mass that flows to our evaporator would be the mass of our R13, and this is the mass of our R12, and this is times the mass of our R13. Okay, so now we derive the COP of our cascade system. Okay, so the cascade system does not compete with the multi-stage system. Okay, so it only provides a vapor compression method for obtaining lower temperatures. So the main thermodynamic disadvantage of a cascade system in the temperature is the temperature overlap in the cascade condenser. So as you notice in the here in the cascade condenser, so this gap here, and this is the temperature overlap. That is the disadvantage of a cascade condenser, but it is used for lower temperatures, and it does not compete with the multi-stage vapor compression system. So the cascade arrangement are applicable to various industrial processes, including the liquefaction of petroleum vapors, the liquefaction of atmospheric gases, and the manufacture of dry ice. So that's all for the discussion and the analysis of our theoretical cascade vapor compression cycles. Thank you for listening, and see you in my next video, and we'll be able to solve some pole problems so that you can fully understand the theoretical cascade vapor compression cycles. Thank you for watching, and don't forget to subscribe.